Assalamu alaikum. In this lecture, I will talk about the time varying fields and write Maxwell's equation. Now, the final thing to do is the Faraday's law of induction, that if you vary a field through a surface S enclosed by a current loop C, then the variation of the flux gives an electromotive force. This is Faraday's law of induction. That's epsilon, the electromotive force, is integration over the contour C of E dot dl, which is minus d1 over C d phi sub m by dt. Phi sub m is the magnetic flux, which is given by integration over the surface S of B dot ds. The minus sign is Leibniz law. And now we can, if S is a stationary surface, we can push the derivative inside the integration. We reach this form. Now using the Stokes theorem, we can convert this into surface integral, which gives curl E dot ds, which is equal to this, to the flux. Now take this to the other side, and this is true for any surface. Therefore, we get curl E plus 1 over C dB by dt equals 0. This is Faraday's law of induction. Now let's talk about the energy in a magnetic field. For a time varying fields, there are induced electromotive forces which cause a source of current to do work to keep the current density constant. The energy in the field is defined as the total work done to establish this energy. Now the power from the source to establish this field, as this the rate, which is dW by dt, is given by minus I times E, which is equal I, instead of E we put d phi by dt, the rate of the flux or the variation. Now in this figure I'm showing the current density where we broken it up to small loops. Each loop has an area delta sigma. We have to convert this I into J delta sigma, or replaced by this. So dW is given by the I times the variation in the electromotive force, which is 1 over C, times the variation in the magnetic induction dot ds. Now we replace I by J delta sigma over C. So the variation in the work is given by this form. Now we use here, instead of B, curl A, and then we replace J delta sigma delta L by J d3x. So we get this final expression for delta W, which is written in terms of the magnetic vector potential and the current density J. But we know that J is C over 4 pi curl H. We substitute instead of J, we get this form for delta W. Now using this identity, we can convert this into surface and volume integral. The surface integral, when we use the divergence theorem for this part, and the integration over a localized distribution, or taking S to infinity, this term gives us 0. So we have left with this expression for delta W, which means that delta W is 1 over 4 pi integration H dot delta B d3x. Now for linear material, we can write H dot delta B as half of delta of H dot B, then substitute here. We get that W is equal 1 over 8 pi H dot B d3x. Now in this slide, I'm defining the self-inductance L, because this is another method to derive the previous relations. If you have a loop here, with the current I. Once you close it, you create a magnetic field. So the electromotive force in this case is given by minus L di by dt. The rate is minus I times epsilon, which is substitute instead of epsilon, we get IL di by dt, which means that W can be written as half I L square. Now we have four equations: divergence D equal 4 pi, divergence B 0, curl E plus 1 over C dB by dt equals 0, and curl H equal 4 pi C over J times J, where the divergence of J equals 0. Now, but from the continued equation, we have divergence equal plus 0 by dt equals 0. And instead of from equation 1, we put divergence d over 4 pi. We get this relation. So we have divergence of j plus 1 over 4 pi del d by del t equals 0. Maxwell replaced j by j plus 1 over 4 pi dd by dt. This is a new displacement, is called displacement current density. So in curl H equation, we have to add this term, which is 4 pi 1 4 pi d by dt. So we get 4 pi over c of j plus 1 over 4 pi partial d by partial t. This is the displacement current. So we get the fourth equation as a modified equation by this term. Now we have these four equations for the time varying field. Now let's talk about vector and scalar potentials. We have divergence B 0. It means that B equal curl of A. If we insert this in equation 3, we get curl E plus 1 over CD by dt, curl A equals 0. Now, which means that curl of this thing is equal to 0. This thing must equal to minus the gradient of the potential phi. Therefore, now E has another term which is minus 1 over CD A by dt. In vacuum, we replace D by A and H by B. So the four equations reduces to this form. Now, from equation 1, we put instead of E minus the gradient phi minus 1 over CD A by dt. So we get this equation in terms of phi and A, and when using equation number 4 of curl B, and instead of B we put curl A, so, and instead of E we put minus the gradient phi minus 1 over CD by dt, we get and use the identity that the curl of curl is nothing but the gradient of divergence times minus Laplacian. So we get this equation. This is equation number 2. Now we replace the four equations by two equations in terms of the scalar potential phi and the vector potential A. So you have these two. If we choose now divergence A, so 1 over C d phi by dt equal to 0, we get two uncoupled equations. Now let's move to what's called a gauge transformation. Since phi and A, there is some arbitrary in these functions, we can replace A by A plus a gradient of some scalar field, and phi is as phi minus 1 over C, a partial this field over dt, gamma by dt, and gamma as it will behave the scalar function. The Lorentz gauge, in Lorentz gauge we use this quantity, divergence A plus 1 over C d by dt is equal to 0. Now suppose A and phi do not satisfy equation 4. Now what we're going to do, we have to replace this A by A prime, which is A plus the gradient of gamma, and phi prime by phi minus 1 over C d gamma by dt, and impose the condition that the divergence of A prime plus 1 over C d phi prime by dt equal 0, and then we look for gamma. Now substitute again the previous equations, we get this expression. We finally reach to this equation, which is Laplace equation. We substitute here in this equation by phi and the gradient phi. we get this term, which del square gamma minus 1 over c d2 gamma by dt square minus this thing. So we need gamma that satisfies this thing. If this is 0, then we get this wave equation, and the condition is still satisfied, what's called a Lorentz condition. This gauge is called Lorentz gauge. A Coulomb gauge, we choose the divergence equals 0. In this case, the first equation becomes the Poisson equation, which is del square phi minus 4 pi over rho, not phi is function of position and time. And the second equation reduced to this form, where still phi is included in the second equation. The solution for the first equation is given by this form, we know this. And then once you find phi, you can insert it here in the second equation and find the vector potential A. That's it for this lecture. The rest of the chapter is easy to follow. It is how to solve the wave equation using Green's function and to go to what's called the Dirac magnetic monopoles, so you can do it yourself. Thank you.